Hello and welcome back, student. Today we'll start with our next topic, that is gas chromatography. The learning outcomes. The learner will be able to explain theory, instrumentation of gas chromatography, discuss derivations and temperature programming in gas chromatography, describe advantages, disadvantages and application of gas chromatography. When we are seeing the history of gas chromatography, the father of modern gas chromatography is Nobel Prize winner John Porter Martin, who also developed the first liquid chromatography in 1950. He has separated fatty acid first time when he has developed the gas chromatographic equipment. The gas chromatography is an instrumental method for separation and identification of chemical compound. Gas chromatography is used to separate volatile organic compound. The organic compounds are separated due to difference in their partitioning behavior between the mobile gas phase and the stationary phase in the column. A gas chromatography uses the flow through narrow tubing known as column, through which the different chemical constituent of sample passes in gas stream, that is called as a carrier gas or mobile phase, which passes at the different rate depending upon their various chemical and physical properties and their interactions with the specific column filling, that is called as a stationary phase, called the stationary phase. As the chemical exit the end of column, they are detected and identified electronically. The rate at which the molecules progress through the column depend upon strength of absorption, which turn depends upon type of molecule and on the stationary phase materials, that is its retention time. A detector is used to monitor outlet stream from the column, the time at which each component reaches the outlet and the amount of that component can be determined by studying this chromatogram. Generally, substances are identified by order in which they emerges or that is eluted out from the column and by the retention time of the analyte in the column. There are two main types of gas chromatography. One is called as a gas solid chromatography or gas adsorption chromatography. Here the mobile phase is a gas while the stationary phase is solid, used for separation of low molecular weight gases. Example, it is used for separation of air components like H2S, carbon sulfides, carbon dioxide, and rare gases, also for separation of carbon monoxides and oxides of nitrogen. The another one is a gas liquid chromatography or gas partition chromatography. The mobile phase is a gas, while the stationary phase is liquid written on the surface of an inert solid by adsorption or chemical bonding and involving the partitioning effect. The principle of gas chromatography is a partitioning. The mixture of component to be separated is converted to vapor and mixed with gaseous mobile phase. The component which is more soluble in stationary phase travels slower and eluted later, whereas the component which is less soluble in stationary phase travels faster and eluted out first. No two component has same partition coefficient conditions, so the components are separated according to their partition coefficient between the gas phase and the liquid stationary phase. Partition coefficient is the ratio of solubility of substance distributed between the two immiscible liquids at a constant temperature. We can demonstrate this chromatographic separation by this diagram, where you can see the separation. Once you have injected the mixture at time t equals to 0 and we are allowing the mobile phase to flow through this column and it is detected by the detector which is placed at the end of column. So at time t equals to 10, we can observe that there is a zone formation. Separate components get separated out into the column. As we go on continuing the separations, the first component, which is having the least affinity toward the stationary phase, will come out through the column, and the component which is having the more affinity toward the stationary phase will be retained into the column. In that way, we can elite out various components by using this gas chromatography. The advantages of gas chromatography were the other techniques. The technique has a stronger separation power, and even complex mixture can be resolved into its constituents. The sensitivity of method is quite high. Even the sample used in nanogram or microgram quantity can be separated by using this gas chromatography. It gives good precision and accuracy. The analysis is completed in a short time, as we know that in column chromatography, which is running by the gravitational force, require more time to separate out every constituent. The cost of instrument is relatively low, and life its life is generally longer as compared to HPLC. The technique is relatively suitable for routine analysis. Allows online coupling with the mass spectrophotometer, so GCMS technique can be used for isolation and identification of substances. But it has various severe disadvantages. It is limited to volatile samples. Sample must be in the gaseous state and should be stable at the working temperature. That is, we are carrying out the separation mostly at 380 degrees centigrade. So the thermolabile substances cannot be separated by using these gas chromatographic systems. Similarly, the biological species like enzymes, amino acid, proteins cannot be separated at this higher temperature. The sample must be soluble and not react with the column. It has a lengthy preparation time for preparation of sample. Many unvolatile substances can be converted to the volatile derivatives, and then they are separated in gas chromatography. It is also a time-consuming column preparation. Activation of column requires a prolonged heating with a continuous flow of gases through the column, and that is also a time-consuming process. The contamination of detector in case of impure samples is a basic disadvantage of gas chromatography, because we are using a very thin capillary tubes as a column and which get contaminated easily. It is costlier than your simple column chromatography, paper chromatography, and thin layer chromatography. Now we'll see what are the various components of a gas chromatographic instrument. The first component we require, that is a carrier gas. So it includes helium, commonly utilized, then nitrogen, hydrogen, argon, which are available in the gas cylinders. The other component is your gas filters, dryer, pressure control valves, and pressure gauges. All are equipped with a gas control panel. The next is your sample injection port, where we are injecting the sample by using the micro syringe or the attosampler. Then next is your column, which may be a 2 to 50 meter long column, and to keep together it is coiled. The column is made up of stainless steel, glass, or Teflon. A separate oven is provided for sample injection port, column, and detector. So oven is the most important component of your gas chromatographic system. Then the detector, various detectors are listed here, such as a flame ionization detector, thermal conductivity detector, electron capture detector, nitrogen phosphorus flame photometric detector, and photoionization detectors. And the last component of your instrument is recorder. So you can see this is the block diagram of instrument and the schematic representation of chromatographic instrument. You can see that there is a carrier gas, then injection port. It is heated to vaporize the sample, then the column, which is heated to control the retention time to maintain the volatility of the sample. Then the detector, it is also heated by a separate oven to keep it clean. Then the data systems and recorders. These are the block diagram components of your gas chromatographic instrument. The schematic representation shown here, it includes carrier gas supply, which is there in the either in the gas compressed gas cylinders, or we can have the gas generators. Then there is a two-stage pressure regulator, which will regulate the pressure of your system, and it will show the gases which is there in the cylinder. Flow controls to maintain the flow of appropriate ratio. Then a rotometer to measure the flow rate of the gases which is flowing. Then a flow splitter which will split a small part of your carrier gas which is directly reaching to the detector, and one part will go to the column. So the compensation of your carrier gas can be carried out by using this detector. There is an injection port through which the sample is to be injected by using the hypodermic syringes, gas-sealed syringes, and the sample will be converted to the vapor plug, which is carried into the column where the separation will take place, and the separated components will enter the detector. A column is also provided with the oven. So this detector, it is having entry for your carrier gas as well as the samples. So attenuation of your carrier gas compositions will take place here, and the signal which is produced is electrically amplified and recorded as a gas spectrum. So we'll see one by one components of your gas chromatography instrument. First is your carrier gas. So ideal characteristic of carrier gas include it should be chemically inert, should not react with the sample and the stationary phase, should be suitable for detector to be utilized and type of sample to be analyzed, should give best column performance with desired speed of analysis, should be readily available, cheap, and pure. It should not cause a risk of fire and explosion hazards. So various recommended carrier gas, which is used in gas chromatography, are shown in this table. You see this general detectors. The type of detectors will decide what type of the carrier gas to be utilized. TCD, we can use helium, hydrogen, and nitrogen. With FID, we can use nitrogen, hydrogen, and helium. In NPD, we can use helium and nitrogen. In ECD, we can use nitrogen and argon methane mixture. With PDD, we can use helium as a carrier gas. Some special detectors require helium with the mass spectrophotometric detector, or IR utilizes nitrogen as a carrier gas. So these are the various carrier gas used in the gas chromatographic instrument, which depends upon the detectors which is employed. The flow rate depends on type of column and temperature of the column. So for the packed column, 25 to 100 ml per minute flow rate is desirable. For the capillary column, flow rate is less than 1 microliter to 1 ml per minute. Flow rate will decrease as the column thicknesses increases. Viscosity of carrier gas has decreased with increase in temperature. So all characteristic of carrier gas must be considered when we are selecting the flow rate. This is just for your understanding purpose. I have given the various gas cylinders with their color identification marks for gases which are used in the gas chromatography. The gases which are used in gas chromatography are chromatographic grade. They are 99.999% pure, and their grading is written on their label, either 99.997 or 999. So all chromatographic gradings are written on the surface of your gas cylinder. So argon, see this belt which is there. So argon is having a cylinders of silver color with the green belt. Then krypton, xenon, radium, and air, which is having a silver color cylinders with the greenish belt on the surface. Oxygen, blue cylinders with white um, belts on the surface. Acetylene is having the brick red color cylinders. Then carbon dioxide, there is no belt, only the grayish color cylinders, silver color cylinders are available with the carbon dioxide. Nitrogen, it is having the black neck belt. Then helium, it is having brown belt. Then flammable mixtures, they are generally having the red belt on the surface, and hydrogen, it is having also the red belt, and whole cylinder is of red color. So it is explosive, so it is to be handled carefully. Then we see the carrier gas flow controls and regulators. Generally, we are having these two-stage regulators. The cylinders are fitted with a gas tank with pressure controller and a two-stage regulator, which will show you the pressure of your gas cylinders and pressure of your system. So it is with diaphragm type of the gas regulators. Handling of this regulator is typical. A pressure gauge that indicates the pressure of a molecule, a pressure of your cylinder or the pressure of the system. A molecular sieves to transfer, filter, dry the gases are used. See, this is the gas control panel utilizing the molecular sieves and the dryers or scrubbers. And this is the oxy trap, which will trap out the oxygen which is there in the carrier gas. It will filter the carrier gas, and the filtered, very highly pure carrier gas will reach to the column. Commonly used carrier gas, as we are discussing, that is hydrogen, helium, nitrogen, and carbon dioxides are commonly utilized. Hydrogen has low density and better thermal conductivity. However, it reacts with unsaturated compound and is inflammable and explosive in nature. So its use will be limited. Nitrogen is inexpensive, but it gives reduced sensitivity with many substances. Helium is the most preferred gas, having good thermal conductivity, but it is expensive. We will see the rest of the chapter in next video. Here it is the end of part 1 of gas chromatography. See you in part 2 of gas chromatography in next lecture. Thank you and happy learning, dear students.